Hello, everyone. Welcome to Developmental Psychology, DEP 2004. I am Dr. Rivera. In this part, I'm going to go over the parts of the brain. And I'm going to specifically talk about this part does this and that part does that. But first of all, I want to go over some divisions. The first division you see there in red is the brainstem and the cerebellum, which we often call hindbrain. You share this with almost everything that is an animal, including fish and reptiles and birds and amphibians and obviously mammals. Almost everything that is an animal that moves is going to have a brainstem. Not everything. Sea stars that move, they don't have a brainstem, but almost everything you think of as an animal is going to have this. Without this, there's a good chance you're going to die. Now, in that light purple slash lavender, you see the limbic system. And your limbic system is a lot of how your memories are controlled, your emotions, a lot of habits, especially physical behavioral habits. You're going to share this with things like reptiles and birds and obviously other mammals. And then your neocortex, which is usually what we think about when we think about the brain, is all that wrinkly part. This you share with birds and other mammals. Reptiles have small portions of neocortices, but they're not by any means as large as ours or as mammals. Now, what you're seeing here is the difference in the frontal lobe between a human and a cat. In the cat, you'll notice that a cat obviously has a frontal lobe, but their frontal lobe is not as thick, is not as large as ours. Um, it's so small, in fact, that it doesn't even cover the brainstem completely. You can still see the cat's brainstem in front of the frontal lobe. But the human brain isn't like that. The human brain, the frontal lobe is enormous. This is in a lot of ways what makes humans is this large frontal lobe. Now, let me start here with the hindbrain. In the hindbrain, you have your medulla. Here is your brainstem, okay? And it's kind of the lower portion of your brainstem before you get to the spinal cord. Without your medulla, you would die. Is your medulla that keeps you alive. It controls all of your vital bodily functions, including breathing, your heart rate, a lot of your reflexes. If you damage your medulla, it is very difficult for you to stay alive. Um, Non-fatal damage, so that's going to be like partial damage to a specific part, might include things like numbness, paralysis of a whole chunk of your body, difficulty swallowing, for example. Now, it's very complicated to think about each part of the brain, this little chunk and that little chunk. So I often like to include little characters that help you to remember. And I think of my medulla as the doctor of the brain because it's your medulla that keeps you alive. It controls your heart, it controls your lungs, and all the things that your doctor usually looks for to make sure that you're staying alive. Now, if there's a doctor of the brain, then there has to be a nurse. And your nurse is going to be your pons. Your pons were still here in the brainstem. And you'll notice that there's this little piece that kind of sticks out like a belly, like a fat belly. That's your pons. And your pons also regulates certain vital functions, motor control, sensory analysis, including sleep, arousal, involuntary breathing. If you were to damage your pons, there's a good chance that you're also going to die. Uh, when you damage it in mild ways so that it doesn't kill you, it's still incredibly dangerous. For example, you might become unable to breathe unconsciously. So now every single time you breathe, then you have to think about it. There's never going to be a time when you're not thinking about it and you're just breathing automatically. Your pons controls that. And without your pons working correctly, then all of a sudden you can't do that anymore. As I mentioned, my pons here is the nurse because she checks up on you and does a lot of the heavy lifting of keeping you alive, making sure that all the sensory stuff works, making sure that you're breathing while you sleep. This is our nurse of the brain, your pons. Now, if you look right behind the brainstem, there's this slight spongy piece that is called the cerebellum. The cerebellum is kind of like the athlete of your brain. This is still part of the hindbrain, but this helps you with coordination and balance. Things like playing a sport, jumping around, spinning, but also simple things like, getting your pencil to get on the line as you write, hitting that key on your smartphone so that you hit the letter that you want. This is part of coordination and balance. And if you were to damage your cerebellum, you would be damaging that. You would lose coordination, inability to judge distances, inability to perform rapid movement changes. So, for example, let's say that I'm studying and I'm writing something and then I'm changing to look through the book to find a specific thing, right? Well, that change of movement from writing to looking through the book, shifting pages, that would be very difficult to make that change rapidly if the cerebellum is destroyed. Other movements would be messed up, a staggered walk, a wider stance, because obviously balancing would become difficult. Now you'll notice that my characters there are an athlete, a dancer, because obviously the quick movements, the changes in movement required a great deal of balance and coordination. Now I want to talk a little bit about the limbic system. Your limbic system is in the center of your brain. So you're seeing the brain here kind of split in half, and the limbic system is right in the middle. And everything that's on the left hand side is also going to be on the right hand side. So it's just like your neocortex that has two parts to it. In your limbic system, the first part that I want to talk about is the amygdala. And your amygdala is this little reddish almond shaped sort of ganglion. And your amygdala helps you with emotions, specifically strong emotions like excitement, fear, anger, anxiety, and memories about fear and anxiety. So let's say that when you were a little kid, you got stung by a bee. And so now you're afraid of bees, right? Your amygdalas don't remember the time that you got stung by a bee. It's not like the memory is in there. Your amygdalas remember how to react to that. And so if you see a bee, now you're an older person, you see a bee, your amygdalas turn on the correct reaction. That is the fear reaction. And so sometimes people see memories and they think memories like, I remember the one time that this happened. No, not those kind of memories. Your amygdala is memories about the reaction. If you were to damage your amygdala, then you would lose the ability to feel emotions correctly. You might forget or not react appropriately. Research suggests that people who have minor damage to certain parts of the amygdala don't know how to assess risk correctly. And so they'll take big risks for things that have very little payoff. The character I chose here is an elephant because you might have heard the phrase, an elephant never forgets. And your amygdalas are like that too. Let's say that you got stung by that bee when you were 5 years old, and then you never saw a bee again, never even read about a bee in a book. But now you're 23 and you see a bee again. Well, your amygdalas remember that you're supposed to be afraid of bees, and they will trigger the fear reaction. Even though you don't remember the time that you got stung by a bee in this hypothetical scenario, you don't even remember what a bee is because you never learned about it in school. But your amygdalas will still remember that you're afraid of those things and it will trigger the fear. So that is what I chose, that an elephant never forgets. Now, your hippocampus, if you look at this little green ganglion, it looks like a little worm. This is your hippocampus. And again, you have two, one of each hemisphere, and it's located in your limbic system. And this is how you control the creation of memories. Now, if you are a bird or a crocodile or a sea turtle or even a person, there are a few memories that are actually located in the hippocampus. And those are specifically memories about spatial memory. So, for example, sometimes you're driving and you kind of space out and you realize that you meant to go to your friend's house, but you started driving to school, right? That's because your hippocampus kind of took over and it remembers what things look like. And you just sort of start driving that way. All right, you just start following that spatial path. Maybe you know how to get to Valencia. If I tell you to drive to Valencia, you know how to get in a car and get to Valencia. But if I ask you to give me the directions to Valencia, sometimes you're like, oh man, what's that street called? Oh man, what's there? What's a land sign that I could think of? Um, because to tell me the directions, that's frontal lobe stuff. That's analysis and putting things into words correctly. But the spatial movement, that's your hippocampus. You remember how to get to Valencia, and so your body just does it without you thinking about it too much. Now, your hippocampus also helps with other kinds of memories, and those memories are actually located in your neocortex. If I tell me about your prom, what dress did you wear? What suit did you wear? What music were they playing? If you remember, those memories are actually located in your neocortex, in the wrinkly portion of the brain at the very top. But your hippocampus is still involved in that. Specifically, it's involved in finding it. Your hippocampus sends connections to your neocortex. And when you remember something and you practice that memory, then it strengthens those connections. And so it makes it easier for you to remember that specific event later because you've strengthened that connection. That's what studying in part is. When I tell you to study for something and you go over the topic, you go over the example, you go over the definition, you go over the question in the packet. Well, what you're doing is you're strengthening the connections between the hippocampus and the neocortex so that hopefully when you read the question in the test later, that the hippocampus can turn on that memory automatically because it's already strengthened. It doesn't have to find it throughout the neocortex. Now, if you damage your hippocampus, the main thing that's going to happen is you're going to lose your memory. If you've ever seen the movie 50 First Dates with Drew Barrymore, where she repeats the same day over and over and over again, what she damaged there was probably her hippocampus because without her hippocampus, she can't create new long-term memories. There was another character in that movie that could only remember about 10 to 30 seconds. That's a real thing that does happen. And usually these people, the damage occurs in their hippocampus. If you know someone who smokes too much marijuana and they are always forgetting things, where are my keys? And their keys are in their hand. It's their hippocampus that is being affected. Marijuana, the chemical that makes you feel high, is similar in shape to a chemical that naturally occurs in your brain. And we call those cannabinoid neurotransmitters. And so the THC can attach itself to the cannabinoid neurotransmitter receptors in your hippocampus. But because it's coming from the environment, it's just a marijuana smoke, then it turns on the hippocampus just sort of randomly. And so now it affects your memory. Also, if you know somebody who's much older and they're very, very forgetful, that also has to do with the wear and tear of the hippocampus. Specifically, people who have very difficult lives, they're very stressful lives, stress damages the hippocampus. Chemicals like norepinephrine and cortisol will damage the hippocampus. And so, if you have a very difficult life, a very stressful life, when you're older, you're going to have more damage to your hippocampus than someone who had a very good life, a very easy life. And so that's going to mean that this person is going to have more memory issues than someone who had a very easy life. Now, doesn't necessarily have anything to do with things like Alzheimer's. Sometimes people ask that question, is this related to Alzheimer's? Not necessarily. In Alzheimer's, there is specifically a type of plaque that builds on the neurons and then sometimes kills the neurons because it kind of builds on top of them. And so that can happen on the hippocampus, but that isn't related to the normal wear and tear of the hippocampus, which also creates forgetfulness. Now, the character I chose is the librarian. When you go to a library and you ask the librarian for a book, the librarian doesn't have the book inside her. The same way the hippocampus doesn't have the memory inside the hippocampus. But the librarian knows where to find the book in the library. And so she can take you to the part of the library where the book is. And sometimes you could just give her a topic and she knows how to find a book that can help you with that topic because she knows her way around that library. Just like the hippocampus. The hippocampus will help you find the memory in the neocortex to turn it on for you. Now, your hypothalamus is directly under your thalamus. That's what hypo means, just under. Your thalamus is this X-shaped thing, and your hypothalamus is this little beak-looking part of the brain. And your hypothalamus is your master gland. It controls all of the other glands. And so as a result, all of the hormones of your body. And so because it controls your hormones, it controls anything that has to do with hormones, homeostasis, your ability to maintain a stable balance in hormones, and then physiological responses like emotions, your body's physical emotions, not your mental emotions like, oh, I think I'm sad, but your body's response, muscle tension, how fast your heart's beating, whether you feel, sort of gross in your body or light, um, thirst, hunger, sleep patterns, a lot of your autonomic nervous system things. All of those things are controlled through glands, and so therefore they're controlled by your hypothalamus. An obvious version of this is puberty. When you are around 8 to 13, your hypothalamus notices that you have enough fat built up in your body. And if you have enough fat built up in your body, then your hypothalamus will trigger the puberty. What it does is that it sends a signal to the pituitary gland via hormones. And then your pituitary gland sends signals to the ovaries if you're a lady, or it sends signals to the testes if you're a gentleman. And the ovaries release estrogen, which begin the process of puberty for girls, and the testes release testosterone and androgens, which begin the process of puberty for boys. Now, my character here for the hypothalamus is like a CEO. If a CEO wants the workers to do something, it doesn't go find every worker in the company and tell them what to do. It sends a signal down. So the CEO might tell the CFO or the COO, and then those executive managers will tell the middle managers, and the middle managers will tell the frontline managers what to do, and the frontline managers will tell the workers what to do. So it's this sort of cascade process of information. And that's the way your hormones work. Your hypothalamus sends a signal to one gland, that gland sends a signal to another, until the right hormone is released, and then the body does what it's supposed to do. Now, I want to talk a little bit about the neocortex. The neocortex is the part of the brain we mostly think about when we think about the brain. It's the wrinkly part on the top. And so I want to talk briefly about the lobes, and then I want to talk a little bit about some of the further divisions. So I want to start out with the lobes. Your occipital lobe is on the back of your head. It's your neocortex in the back of your head. You have two of those, one in your left and one of your right. And your occipital lobe controls visual information. You'll notice here that I chose a digital producer, right? Because it's your occipital lobe that draws the picture that you see in front of you, right? When you're looking out and you see your computer, your kitchen, your room, whatever, right? Your friend in front of you. Um, the picture that you're seeing is drawn by your brain. Our eyes send information to the brain, but it's not our eyes that draws the picture. You'll notice this. If you ever take a movie, let's say you turn on your camera in your phone and you walk as you are taking a video, when you play the video, you'll notice that your video bounces as you walk. But that doesn't happen when you are just seeing, right? Your brain doesn't do that to you. That's because your eyes send the right information, but your brain just paints a still picture in front of you. So it doesn't have to take in account the constant movements. Um, it's also why sometimes you see things that aren't there. Sometimes your eyes might sense something that's a little distorted in the periphery, or maybe it's dark out, or maybe you drank a little too much, or you've taken a drug. And now your brain paints in something that's not there at all, a monster. Maybe if you're taking a drug, you might see a monster that's not really there. It's because your brain painted in a monster. And even though your eyes don't see that, your brain still painted it in. And so you see it. You might have also noticed every once in a while, you're looking for something, let's say in your room, and you look for it and you look for it and you look for it and you don't see it. And then you come back a few hours later and it was right there. And you go, how didn't I see this? It was right there. Again, it's because your eyes play a part in creating vision, but they're not the most important part. The most important part is your occipital lobe who draws the picture. And so while you were looking, even though your eyes were clearly picking up the information, your brain never painted it in. And so you didn't see it right in front of you. If you damage your occipital lobe, obviously you're going to have visual problems, problems locating things in the environment, hallucinations, inaccurately seeing objects, things like word blindness might occur where you can't think of the right word, um, things like that. Now, your temporal lobes are on either side of your head, kind of right above your ear, or I should say right behind your ear. And you can see it there on the spinning brain. Obviously, you have one on either side. Um, your temporal lobes control hearing. If right now, as I'm speaking to you, it's your temporal lobes that can hear the cadence of my voice, how loud or high or low or raspy or pitchy my voice happens to be. When we talk about understanding language. Right now, I'm speaking to you, and you don't just hear the sounds I'm making, you understand those sounds as concepts, as a meaning. And only one of your temporal lobes can do that, and that is your left temporal lobe. You can hear with both temporal lobes the cadence, the loudness, etc. But understanding language only exists in your left brain, and specifically in the part that we call Wernicke's region. In your right temporal lobe, you have another part called the fusiform gyrus, which helps with faces. If you were to damage your temporal lobes, obviously you would have a problem understanding words, verbalizing or identifying objects with words. The character I chose here is Mel Gibson in the movie What Women Want. I think there's a new movie called What Men Want. And in that movie, Mel Gibson can hear women's thoughts, right? So hearing women's thoughts, that would happen in the temporal lobes, even though for him, it has nothing to do with his ears. Um, The temporal lobes are the part of the brain that hears and creates the meaning and sound. If you were to put your hand in front of your forehead or on top of your forehead and just spread out your hand as far as possible, this is your frontal lobe. If there's a part of the brain that's you, this is the part of the brain that's you. This is your personality, your hopes and dreams, your goals, your ability to have self control, your ability to move your body voluntarily, your ability to speak, problem solving, perception of self, impulse control. This is all your frontal lobe. If I were to damage your frontal lobe, there is a good chance that you would no longer be you. You wouldn't think like you wouldn't feel like you. Uh, Other people would recognize your face, but they would not recognize your personality. And they would say things like, that is not Jenny anymore. That person is no longer the Jenny that I used to know. Depending on which part of your frontal lobe you damage, you might also cause paralysis, problems with self control, especially if you damage your prefrontal cortex or your anterior cingulate. Changes in personality also would be part of your prefrontal cortex and anterior cingulate. Because one of the things your frontal lobe does is it controls your limbic system. Your limbic system without your frontal lobe is very animalistic. It would be angry and sexual. Um, it would be maybe even violent, hungry all the time. It would have a hard time focusing and paying attention. And so your frontal lobe comes in and it controls that. Think of a chariot rider controlling the horse. All of a sudden, your frontal lobe controls your impulses and then can guide them the way that it wants them to. The characters that I chose here are Pinky and the Brain because, first of all, they're smart mice. And even though one of them is smarter than the other, even Pinky is quite smart. He can speak and he has executive functions and they have goals. They want to take over the world and they have unique personalities. Pinky is very caring and he cares a lot about Brain and his emotions. And Brain, on the other hand, is a little bit more cold and calculating. Either way, their personalities are highly controlled by their frontal lobes. Now, if you were to put your hand on the top of your head towards the back, that is your parietal lobe. And your parietal lobe controls the sensation of touch. Right now, if your shoes are a little too tight and you can feel that, if you pass your hands over your shirt and it's soft, or over the table and it's hard, maybe something is rough versus smooth, that sensation of touch, that's your parietal lobe that does that. There's a specific part of your parietal lobe that helps you to determine that. Now, there's another thing your parietal lobe does, which is the sensation of passing time. For me, I've been doing this video and it feels like it's been like 5 minutes from when I started. But if you've been listening, especially if you're not very interested, it might feel like I've been here for a few hours already. That's because I am in flow and I am very focused on what I'm doing, time feels like it's going really fast for me. Where as for you, because you're trying to pay attention and you're not sure when it's going to end or what I'm going to talk about next. And again, if you're not very interested, it feels like time is dragging on. So there's another part of the brain that gets affected with marijuana. Sometimes when people smoke marijuana, time seems to get slowed down. That's your parietal lobe that's being affected there. If you damage your parietal lobe, you're going to have problems with recognizing parts of your body. For example, if I tell you, touch your elbow, you might not be able to grab your elbow correctly. Or if you do, or if I touch your elbow and I ask you, what part of your body am I touching? You might say, my thumb. Because your brain now doesn't recognize your body correctly and it doesn't know which part is sending the right signal. My character here is the Flash. You could imagine that as the Flash is running, you can feel the wind on his face, the ground on his feet. But also, if the Flash runs fast enough, he can time travel. And so the Flash can feel the world around him, he can feel the speed force, but he can also control time, or at least time travel, kind of just like your parietal lobe. All right. Now I want to talk about just a handful of divisions, smaller divisions of the brain. And so I want to talk here about your somatosensory cortex and your motor cortex. Your motor cortex is in your frontal lobe. You can see here is your motor cortex, and your somatosensory cortex is part of your parietal lobe. But these two parts of the brain work together to have movement and sensation work together. Specifically, if I were to grab a cup of soda that's filled, well, my somatosensory cortex would help me understand that the cup is heavy. And so, therefore, it would send a signal to my motor cortex to hold the glass tighter, right? Because my motor cortex controls the movement of my hand, while the somatosensory cortex feels the sensation of touch. Maybe my cup is too cold, it has too much ice, and after a while, it starts to hurt my fingers because the ice is too cold. And so my somatosensory cortex will tell my motor cortex to put the glass down. And so there's always a back and forth between these two. And another important aspect of your motor cortex and somatosensory cortex is that they both have what we call point-to-point mapping. That is, the part of your brain that moves your pinky is the same part of my brain that moves my pinky, right? They all, your brain essentially moves your body in the exact same way that my brain moves my body. There are exceptions to that. Maybe you're a great dancer and you devote a slightly larger portion of your brain to your knees. And because I don't dance, well, I just don't use my knees like that. And so I devote less space in my brain for my knees. Um, uh, but there are certain parts of your brain that we just use or that we have to devote a great deal of space for. For example, your hands. You use your hands for a lot of things: holding a pencil, typing, punching, I don't know, grabbing groceries, just all types of things. And so you have to devote more space in the brain to have all of that programming of how to control the hand. On the other hand, uh, my back is very large compared to my hand, but I devote very little space to my back. If you look at the picture here, you can see the hand is very large. That's because we devote a large part of the brain to the hand. But over here for my torso, it's just a very small portion of my brain devoted to my torso, and even smaller for my back specifically. That's because I don't use my back. I can feel it, but I don't have the need to move it in very specific ways, especially with the skin. Um, and even the muscles there are used very specifically. There's not very big movements. Now, let's say you're a gymnast and you do use your back to jump from one uneven bar to the other. Well, all of a sudden, you use your back in a more complex way than I do, and so you would devote more space to that than I do. Now, when we talk about language, language exists almost entirely in your left brain, and there's a few parts that help you with language. In your frontal lobe, you have Broca's region. And Broca's region helps you to create language. Right now, when I'm speaking to you, uh, I am using Broca's region to find the right words and say them out of my mouth. But also, if you're writing me an email or you're writing down notes, you still use Broca's region to find the right words and to think about the right concepts to write them down. If you speak in sign language, Well, even though you're not using your mouth, you still use Broca's region to sign and to find the right words, etc. In your temporal lobe, you have Wernicke's region. And I know it's spelled Wernicke's with a W, but it's Wernicke's region. And Wernicke's region helps you to understand language. Right now, as I'm speaking to you, you aren't just hearing sounds. The sounds I'm making mean words to you. And they not only mean words, they mean concepts and ideas. And that is Wernicke's region that does that. If I were to damage, or if you were to damage your Wernicke's region, you would not be able to understand my words. You would still hear the cadence of my voice and the loudness and how pitchy or deep my voice is, but you wouldn't hear the words. The opposite with my Broca's region. With Broca's region, if I damage Broca's region, I would still be able to understand you. But when I spoke to you, I wouldn't make words. I would just make sounds to you. In the parietal lobe, you have your angular gyrus. And your angular gyrus helps you bring a lot of information together so that you can read. Information from your occipital lobe, when you read, there's words on a piece of paper that you're seeing. Well, that's coming in through your occipital lobe and it gets to your angular gyrus. And you have to find the right words. You have to find the right words in your Wernicke's region. And you have to be able to create language from Broca's region. And then you have to be able to understand the concepts, the larger concepts of what you're reading. And that's going to be other general things or general parts of your frontal lobe and your parietal lobe. And all of that comes together in your angular gyrus, which you can see here is labeled as reading comprehension in that yellow portion in the parietal lobe. If you were to damage this, then you wouldn't be able to read or read as well. In fact, what we find is that people who have reading comprehension problems often have issues with their angular gyrus or the connections to their angular gyrus. You can damage these in a lot of different ways. If you have a stroke to a specific portion of the brain, you might damage it. You might damage Broca's region or Wernicke's region or your angular gyrus. Or maybe you don't learn. Let's say your parents misplaced you when you were 2 years old and you lived in the jungle by yourself and I don't know, some wolves raised you. Well, you would never develop your Wernicke's region correctly. And so if as an adult we found you, humans found you, we would never be able to teach you language. And so I might be able to teach you to say water when you're thirsty or food when you're hungry. But this conversation, this thing where I'm just like saying words to you and you just understand what I'm saying, that could never happen because the Wernicke's region didn't develop correctly. Sometimes people get really upset with this because it means that Tarzan could never happen. For Tarzan to have occurred, right? You leave a kid in the jungle, he must have already been like 8 to 10. Otherwise, he would have never developed language. So you couldn't leave Tarzan as an infant in the wilderness. Let me tell you one more thing about Wernicke's region. Sometimes you tell your dog that you're going to go for a walk, and he gets really happy, and he'll go grab his leash and go to the door because he knows what you mean when you say walk. He also knows what you mean when you say bath, and he runs underneath the bed because he understands you. And what part of your dog's brain is your dog using when he hears the word bath or when he hears the word walk? Wernicke's region, just like you. The difference is that your Wernicke's region is very thick and your dog's Wernicke's region is not very thick. Ours is just more highly developed. All right, everyone. Thanks for watching. Let me know if you have any questions. And remember that the best way to contact me is directly through Canvas. I hope to hear from you soon.